Alright, welcome back everyone to another AMC tips and tricks video. Today we're going to be covering the basics of exponents and logarithms. So we're going to start with the easier one, which is exponents. So I'm going to start with the very basics of exponents. So first, what is it? Well, suppose you have, let's say 2, and you have a string of 2's multiplied together. Well, this is really tedious to write, so we have a shorthand for this. Basically, we count that there are 6 2's over here that are multiplied together. So instead of writing 2 times 2 times 2 times 2 times 2 times 2, we write this as 2 to the power of 6. You might have seen this before. This is a very neat shorthand for a lot of various functions and expressions. Alright, so the first thing we're going to cover is a few examples to calculate some exponents to get you familiar with this concept if you're not already familiar with it. 2 or 3 examples should suffice in this case. So first let's calculate, say, 5 to the power of 3, or 5 cubed. Well, this is simply 5 times 5 times 5. There are 3 of these 5's over here. And this is equal to 125. And next up, let's say 2 to the 8. So this is simply 8 2's multiplied together. And you can find that this is equal to 256. And last one, we're going to do 1 to the power of 7. Well, you quickly realize that 1 to the power of anything is equal to 1. So that is pretty simple. But of course, this isn't all there is to exponents. There are many rules that we're going to cover here today, and I'm going to prove all of these rules by going back to the definition of exponents, basically a really long product. And the first rule is if I have a number a to the x times a to the y, so there are a number of rules that we're going to cover here, and I'm going to prove all of these rules by going back to the definition of exponents, basically a product. And the first rule I'm going to cover is if you have an instance where you have a number to the power of x times the same number to another power, y, and we want to simplify this. Well, the simplification is a to the power of x plus y. And we can show this by simply noticing that a to the power of x, this is simply a times a times a times all the way a, and there are x of these a's, and a times y is the same thing, but with y of these. And obviously, there are a total of x plus y a's in this product, and so a to the x times a to the y is equal to a to the power of x plus y. The next rule is very similar to this one. If you have a to the x divided by a to the y, you can very easily show that this is equal to a to the x minus y. So I'm not going to prove it here. The next rule is when you have a to the x and you raise this number as a whole to the power of y. This is obviously a bit different from the previous ones, but we can write this as a to the x times a to the x times a to the x, so on, times a to the x. And there are y of these a to the x's. And according to the product rule, where a to the x times a to the y is equal to a to the x plus y, we can very easily simplify this expression to a to the x times y, like so. Okay, the next rule is when you have a product of numbers and you raise this product to a exponent. You can simply separate the exponents like so. So a times b all to the power of x is equal to a to the x times b to the x. Similarly, you have a over b all to the x is equal to a to the x over b to the x. I'll prove the first rule over here. So writing this out, we simply have AB times AB times AB times so on. And there are x of these ABs. Well, we can put the A all together and the B's all together, and we'll get A times A times A, and so on, times B times B times B times B, so on. And each of these, obviously, there will be XA's and XB's, and so the left-hand side is equal to the right-hand side over here. And the second rule can be proven similarly. All right, next up we have a different rule from the previous ones. If we have a number, a, to the power of 0, well, what is this equal to? Unlike previous instances, we can't write this as a product of a's because there are 0 a's to multiply together. So how do we define this? Well, going back, we can look at a few examples. So if we have, say, a cubed, then we see that a squared is equal to a cubed divided by a. And if we have a squared, then we see that a is equal to a squared divided by a. And if we look at a, then we can say that a to the power of 0 is equal to a over a. And so this naturally defines a to the 0 as 1. Now there is one crucial exception here to this rule. A cannot be equal to 0. 0 to the power of 0 is actually an indeterminate expression, meaning that it doesn't have a value that we can give to it. And you should be really careful whenever you see this expression. And this ends our introduction on exponents. We're going to move on to logarithms next. So now we're going to talk about logarithms, which are closely related to exponents. So first I'm going to explain what logarithms are. Let's first take an example. So we know that 2 cubed is equal to 8. Well, let's say that you don't know that. Suppose that you want to figure out, okay, I want a value of a such that 2 to the power of a is equal to 8. And I want to know what a is. Well, there is a way to write a out, and it is simply written as so. Basically, what I'm saying here is a is equal to log base 2 of 8, and this means that if I raise 2 to the power of a, I'm going to get 8. So these two expressions mean exactly the same thing. We just developed this version of writing it so that we can isolate the exponent a. Alright, as another example, we know that 5 to the power of 4 is equal to 625. So we can write the exponent by itself, 4, is equal to log. This time the base is 5, so log base 5 of 625. So 4 is equal to log base 5 of 625. And this means that if I raise 5 to the power of 4, then we get 625 as our answer. So similar to exponentials, we have a lot of rules for logarithms as well. The first rule is similar to the product rule for exponentials. So as a reminder, that was a to the x times a to the y is equal to a to the power of x plus y. So for the logarithm version of this rule, let's say that a to the x is equal to b, and a to the y is equal to c. Then we have the equation bc is equal to a to the power of x plus y. And of course, we can write x equal to log base a of b, and y is equal to log base a of c. Remember, this statement is saying that x is the power we need to raise a to get b, which is exactly this statement. So we can rewrite this top equation as b times c is equal to a to the power of x, which is log base a of b, plus y, which is log base a of c. And now we see that we can write the statement log base a of the product b times c is equal to log base a of b plus log base a of c. And we can write this because essentially what we're saying is the right-hand side is the exponent we need to raise a to get b times c. And we see that this is exactly the same statement as this. And since this is the same equation as this, we have that this is always true. And written more neatly, we have that log base a of x times y is equal to log base a of x plus log base a of y. Now you may also recall that the quotient rule for exponents states that a to the x divided by a to the y is equal to a to the x minus y. Well, the same rule, but in logarithmic form, would be log base a of x divided by y is equal to log base a of x minus log base a of y. So this is, again, really similar to the product rule, but instead with a minus sign. The next one we're going to cover is the power rule. So if we have log base a, but instead of log base a of x, we have log base a of x to the power of n, for some number n. We can simplify this as n times log base a of x. And this is apparent because we can write the left-hand side as log base a of x times x times x times so on, with n of these in here. And of course, according to the product rule, each of these is log base a of x. And there are n of those, which means that we can write this as n times log base a of x. You can also prove this by morphing the power rule of exponentials, and it will get this rule eventually. The next rule is more of a smaller rule that I'm going to show in preparation for the rule afterwards. So this rule stems directly from the definition of logarithms. And the rule states that a to the power of log base a of x is equal to x. Now this is real clear because log base a of x is the number we define that when a is raised to this power, we get x. So essentially this is a restatement of the definition of a logarithm. So you can remember that this statement is always true. Now we're moving on to the last and most complex of the rules with regards to logarithms, and it is the rule of the change of bases. Now we're going to move on to the last and most complex of the rules for logarithms, and it is the rule for change of base. So I'm going to present the results to you first. We have log base a of x is equal to log base b of x divided by log base b of a. This statement can also be written as log base b of a times log base a of x is equal to log base b of x. And we're going to use this latter form to prove this theorem. Okay, so to prove this theorem, we're going to look at this expression, and we're going to have b raised to this as the exponent. So first, we can write that this expression is equal to b to the power of log base b of a, all to the power of log base a of x. This is the reverse of the power rule for exponents. And of course, we've shown that b to the power of log base b of a is simply equal to a. And a to the power of log base a of x is simply equal to x. So we have shown that b to the power of this is equal to x. And of course, we can rewrite this as log base b of x is equal to the exponent, which is exactly this theorem here. So we've proven the change of base theorem for logarithms. And this concludes our discussion about the basics of exponentials and logarithms. So thank you for watching, and we're going to follow up with some example AMC problems that deals with logarithms and exponentials.